So let's talk about inheritance with SQL. Right? We had mentioned that there were certain concepts, right, that were very common in object orientation that don't have an equivalent implementation in relational database, right? One of them is inheritance. Right? Inheritance is a very common concept in object-oriented technology, right? But object-oriented technology, relational database predates object orientation. So we already have SQL and lots of implementations for a decade or so before we even thought of the idea of object. Well, actually, not true. We had already had a lot of the research and thinking about object orientation and if we had an intelligent system, how would we explain the world and describe the world to this AI, right? And so there was a lot of research on how to do this. And said, well, what's the world made up of? It's just a whole bunch of objects, right? And objects have properties, and objects can be grouped together into classifications, right? Where you have this hierarchy of objects that can inherit from each other and whatnot. Yes. So yeah, the research was there, but there was no actual implementation of it in language up until maybe when we started looking at C++ and all these new languages that were introducing all these object-oriented ideas. But there was no equivalent in relational databases, right? But nevertheless, we need to see ways how we can twist SQL in such a way that would allow us to model the idea or the concept of inheritance. So there's quite a few different ways of doing it. We're going to look at 3 different ways of doing it. There's three strategies that we can use. One is called the joined or normalized strategy. One is called the single table or denormalized strategy. And finally, the hybrid, by the table per class. Right? So let's take a look at each one of them. Imagine you have this base class question that has different fields that are the common fields for different types of questions. Right? You might have an essay question, a fill-in-the-blank question, and a true-false question. Right? They all have a title. They all have how many points each question is, a description, instructions how to answer the question. Right? But then, essays might not have anything peculiar about essays. Maybe where you might store the answer for that essay. Fill-in-the-blanks might have the actual blanks. Might say that you have to fill out a whole bunch of blanks, right? And then it might name all the blanks and what the valid values responses would be, so that we can compare your answers against the correct answers. So I need to store that somewhere. So we can store it in a string array, or maybe a comma separated list of correct values. Then true and false, we can store whether the correct answer is true or false. And so we can store that in the true-false question. Everybody can? Right? So there's no one way of implementing this in relational databases. Right? There's only half ways of implementing it. Right? And once you choose a strategy, you should stick to that strategy. I believe in the assignment we asked you to use 2 strategies. Right? So we'll take a look at 3 of them, and you're asked to implement 2 of them. Right? So let's first look at the joined strategy. So the joined strategy. I think this might be the more conceptually sound implementation, right? That everybody can agree and understand. It makes sense, right? Usually, what you start off is that you look at the class diagram. It says, oh, there's 4 classes. There must be 4 tables, right? That's kind of the most common way of thinking about this, right? But what that means is that if I add a question. If I insert a question, it's a true-false question. If I insert a true-false question, notice that I need to do 2 inserts, right? I'll need to insert the true-false, the is true. I'll need to insert it into the true-false table, whereas the title, the points, the description, the instruction, I will need to insert it in a different table, right? The question table. Make sense? And somehow I would need to specify, hey, that half of the information is in one table and half of the other information is in the other table, right? Meaning that when I want to reconstruct the table because I need to render it in the quiz, right? I need to go fetch records from both tables, right? I need to say, oh, well, half of the fields are in one table and half of the fields in the other table, right? I need to join them, right, and rebuild the question. Make sense? So somehow I need to have like a foreign key from one going to a primary key to the other. Make sense? Also, what happens if I need to delete the question? If I delete the question, it would make no sense to delete the one record from one table, but not delete the record from the other table, right? Because they are the same thing. They're one and the same. Even though they're stored in two different tables, they really are part of the same, conceptually, of the same question. Yes? Right? If it makes no sense to delete the record from question, but not from true false, they both either both exist or neither one of them exists. Right? You need to treat them as one. Right? So in joint, you would create the base question. Right? Notice my naming convention. They don't have to be called this way, but I call it this way so that I keep track of it in my head. So the joint here is the strategy that I'm using. And then the base question is the class that I'm trying to recreate, right? So I have the base question class has the ID as a primary key, description, instructions, points, and title. So all the fields that are common to all questions live here, right? But the other two tables, right, where we have the true false. In the true false, notice that I don't have the fields that are common to all questions. I have them in the base question has those. I only have the ones that are specific to me, right? Only the is true lives here. But notice that I also have a foreign key, right? A foreign key that is going to refer to the primary key of my parent, right? Of where the description, the title, the points, that's where it lives over there, right? Also, notice here that it's not shown here, but it should be. There should be a cascade delete, right? Cascade delete, meaning that if I remove, right, if I remove the join based question, if I remove the record over here, right, any of my children, right, they should go too. I mean, it makes no sense for me to live, right, for the parents to live and the children to. Wait a minute, what? Oh, no, that's a very dark analogy. That if I remove one of the records, that the other records survives, right? Yes.
Should we cascade update also?
Yes. Yep. Any updates would also cascade. Yep. The so yeah, I'm missing here the cascade here, but it should show here. Same thing for the blank questions. We have the varchar for the variables, right? And I have a reference back to my parent as well. If later on we'll take a look at the JSON representation of these pieces of data where you have the join, where I have only the values for the joined for the base record, and then if I look at the fill in the blanks and true false, right, it would contain the records that are common to everybody, right, that are being taken from the base table. And we are merging it, we're joining it with the records that are from the other table. These are just examples of how it would look like in records, yes? Now, before we leave this example, one of the criticisms of using this strategy, is that, well, here we have a simple inheritance, right, where you have one class A, and which class B is inheriting from, and that's fine, right? Basically, I have the fields, some fields here, some fields in B, and to retrieve them, I need to join these two. I need to join where the foreign key of this is equal to the primary key of that. Yes, that's not too bad. But what if I have another one over here? Right. That means to recreate a record that lives down here, I need to join C with B with A, right? I need to join all the tables in the hierarchy tree, right? And as it's very common in Java and other object-oriented languages, right? When you're architecting this, it's very common to have very deep, right, hierarchies of inheritance. Right? So trying to represent that in multiple tables and trying to join all these tables and retrieve all this would become very, very expensive. Remember that every time you do a join, right, this is retrieving something from here is order n, retrieving something from here is order n squared, retrieving something from down here becomes n cubed. So this could be, n, to the n, how deep that hierarchy is. So this is the most easy to understand and conceptually makes sense, and DBAs preferred with this implementation because it's normal is denormalized. It's normalized, right? And meaning everything lives where it must, but it's very expensive to implement, right? It's slow. So a better solution is to use what is referred to as the single table implementation, right? So the single table implementation is also referred to as the denormalized implementation, meaning we're not going to split this into multiple tables. Instead, what we're going to do is that we're going to do a single table. We're going to have a single table, one big table, right? And what we'll do is that we're going to take some of the fields from one of the tables and put them here, A, right? And then we're going to take the fields from B and we're going to put them in the same table, and we're going to have the columns that are specific to just B, right? And then same thing with C and whatnot, right? Now notice this is the opposite of what we learned about first normal form, second normal form, third normal form, where we were splitting these tables into multiple tables because we want to avoid redundancy, right, and avoid inconsistency. So we're basically going against the best practice. So typically, the way you would do this is that you would not do this manually, right? Instead, you would rely on algorithms, right, such as Java Persistence API or some of these ORM tools that would do this for you, right? It would make sure that that there would be no redundancy, right? That things would be validated for you, and that you would not run into the risk of inconsistency. So you would not do this manually. You would have a tool or store procedures that would do this for you, right? So that when if you insert data into C, then you would be inserting data into some data into A, some data into B, and some data into C. But if you're inserting something into B, typically you would just store in A and B, right? Or if you're inserting something in A, you'd be storing something in there in A, right? And everything else would stay null. Everything else would stay null, right? So null, everything else would stay null. Okay? Now for this to work, right? Whenever you do a query on a particular record, you need to be able to know which of these fields are relevant and which are not relevant. Right? If I'm inserting something in A, all the columns for B and C and all those columns are irrelevant to me. Okay, they're null. Right? I don't need them. Right? So to keep track of what is actually needed, right? To know what was the original intent, right? We would add an additional column. Call it D type or something. A discrimination column, a column that would tell me what was the original data type? Was it A? Was it B? Was it C? What was the original thing that you were storing in here? How should I interpret this, right? So this one would be maybe C, this one would be B, and that one would be A. Make sense? All right, so let's look at the implementation. So here's my single table. There's just one table, and it has all the fields. The fields from the question, the fields from the true false, and the field also from what's the other one? Multiple choice, I think, or fill in the blanks, right? All the fields are there, and notice we have an additional field called D type, right? That kind of keeps track of what was the original intent of this class. Make sense? Right? Now this one doesn't have the problem of joins, right? And performance. Because you're not joining anything. All the data that you need is already in the record. You don't have to go fetch other records in some other table and do the join where the primary key is equal to the foreign key, blah, blah, blah. Okay? You don't run into that issue. Okay? So even though this is popular amongst developers, it's not as popular amongst DBAs, since you're going to have a lot of empty space. Lots of nulls everywhere, right? And DBAs don't like that. But it's for performance reasons, right? We often choose to go this route. And you finally have the what is called the table per class implementation, which is somewhat a mixture of both. Okay, it's a mixture of both, where what you do is that you keep it's kind of the best of both worlds. Where Well, you go back to the having one table per class, right, like we had over here, but instead what we do is that we repeat the fields. We repeat the fields, right? So if you have A, right, that declares a single field, A, right, and then you have B here that inherits from A, so we have B. So B would only declare maybe just B, right, the field B. But we don't want to have to join with A to go fetch this information, right? We want to avoid having to do that. So instead, what we do is that we copy over all the fields from A, we copy them over down, right? So B is going to have A again, right? And then, so these are the inherit fields, right? And this is the my own field, yes? And if you have C, right? If you have C, then you would copy over all the fields that you were inheriting. So you have A, B. These are all the inherited fields, inherited. And then you have my own C column, right? So the way that would be implemented is that you have, the A table would have a single record, a single field A, and then you have, B, having A and B, right? Records in here, and you have C, the C table, having all three, A, B, and C. So this goes back to saying, oh, well, I'm keeping the hierarchy. They're referencing each other, but I don't need to join. I don't have the problem of joining because the data already lives here. The data lives right here. So I have the values A1, B1, C1 without having to go back to any of these, right? So if I insert something in B, a B record, I would only have values in that B table. If I insert an A, I will only have values in A. If I insert something in C, I only insert records in C. That makes sense? Right? I don't have it spread out over multiple tables, right? I already have everything that I need in that particular record. Right, so here it is, base question only has the fields for the base question, whereas the true false has all the fields from the base question plus its own field of is true, and then the is blank, the fill in the blanks has the variables for that are pertinent to it plus the ones that inherited. Make sense? Right? So this is kind of best of both worlds. It's denormalized. I mean, it's normalized, right? So you're not storing the values in multiple places, and also I'm not joining, right? And I don't have any empty spaces, right? So it's kind of best of both worlds. Okay. It's a little more complicated to implement, right? But typically, again, you would use ORMs and like JPA to do this for you. You would not do this manually. Yes. Oh no, if you store C, you would only store in C. You don't repeat it in A or B. You only store in C. So you're not copying this over both places.
So it's almost nothing in B.
Almost no relationship between them. Yep. Yes.
So if you're adding in C, will you add only value for C or the other two bits?
Yeah, no, you would only insert into C. You would not insert into B and A.
Okay, so you will add A and B's values at, the fields
Only here. So you would not insert, you would not repeat it, right? Because we have broken the relationship between them, right? They're all independent of each other.
Yeah. So there will be no foreign key.
Yep. Exactly. I think we talked about portable enums already.